So let us talk about black box testing. So testing software against a specification for its external behavior without knowledge of internal implementation details. So only external is required, no internal implementation details are required in black box testing, and this can be applied to software units, for example classes, or to entire program. Now external behavior is defined in maybe API docs, functional specs, and requirement specs, etc. Since this black box testing purposely disregards the program control structure, the attention is primarily focused on the information detail, that is, what goes in, what comes out. So, the goal is to derive sets of input conditions, or we call it as test cases, that fully exercise the external functionality, or rather, the functionality of the software. Now, black box testing, it tends to find various kinds of error than white box testing, because white box testing also is important and it finds various kinds of errors. So what black box testing does is it finds missing functions, usability problems, performance problems, concurrency and timing errors, initialization and termination error, etc. So unlike this white box testing, this black box testing tends to be applied later in the development process. While if we take a case of white box testing, the developer himself or the developers themselves does the white box testing at a unit level. So what are the information domains? Means actually we are talking about only input and output. So inputs, the individual input values are there. Try many different values for each individual input. This can be the idea. And the combination of inputs means just combine the inputs in various way you want. And ordering and timing of inputs mean which input you want to give first or second, and rather you change the ordering. So this timing also makes a difference. These are the inputs we will be employing in some of our examples. Let us start with this equivalence partitioning. Now we can have innumerable, means infinite number of test cases for a large project. Not I'm saying about a small project, but we can have, just to exaggerate, we can have many test cases that may be tried. So you have to select a relatively small number of test cases that you will actually run. So how to choose them? So equivalence partitioning helps us to answer this query. What we do is we partition the test cases into equivalence classes. So each equivalence class, they contain a set of equivalence tests, means the test cases which are looking equal. So two test cases are considered to be equivalent if we expect or think that the program to process them both in the same way, means they will follow the same path through the code. So there is no point in repeating that. So if you expect the program to process two tests in the same way, let's only test one of them, then we will be able to reduce the number of test cases where we have to run. This is first level partitioning. First we have to see that whether the test is valid or invalid. First we have to partition on the basis of validity. This is the first level partitioning, we call it. This is valid, these are invalid. Now partition valid and invalid test cases into equivalence classes. This is how it is done. We partition them. We partition them means these two test cases are similar. That is why they are in same. They are been marked in the same region. Now just create a test case for at least one value from each equivalence classes. Consider if this region has hundreds of tests and you take out one, so that will be reduced to to a considerable extent. The test cases will be. So when designing test cases, you may use different definitions of equivalence, each of which will partition the test case space differently. Let us take this example. If we want to add n1 to some n2 and some numbers, The equivalence definition 1 says partition test cases by the number of inputs. This means n1, n2, n2. How many numbers are there? Then equivalence definition 2 says partition test cases by the number of signs they contain, whether they are positive, negative, etc. Then equivalence definition 3, what it says, partition test cases by the magnitude of operands, whether they are large numbers, small numbers, or both. So when designing test cases, you may use different definitions of equivalence, which I just showed you. So each of which will partition the test case or test case space differently. Let us take one more example. String fetch URL. So equivalence definition 1, what it says, partition test cases by URL protocol. Which protocol you are using, like HTTP, HTTP, FTP, file. And the definition 2 says partition test cases by type of file you are going to get, means the retrieved file, HTML, JPEG, plain text, whatever. Now equivalence partition 3 says partition test case by a length of URL, whether it is large, short, very long, all those combination. Now let us come down to an example. We have an integer n such that it belongs to, or it is between -19 to 19. What can be the valid equivalence classes and what can be the invalid equivalence classes? For our this phone number, area code, we have prefix, suffix, etc. All this being given. Now from 99 to -10, these are equivalence classes. From -9 to -1, these are also equivalence classes. 0, 1, 9, 10, 99. So what we have done is, we have taken, if you consider it to be a number line, and we have this 0 here, 99 here, and -99 here. So we have covered most of them. Right, from -10 to -19, then 10 to 99, then -1 to -9, 1 to 9, and then 0. All these value and all these combinations, they come under valid equivalence classes. What are invalid equivalence classes? If you say less than -99 or greater than 99, that doesn't exist. And malformed numbers like 12 minus, this doesn't exist actually. Or 1, 2, 3, this is not done. This is not how it is written. And non-numeric strings, because it is expecting strings which are numeric, so this will not work, or any empty value. But you need to check for them as well, because user is named, no voice user. He can enter anything. Even if you say him that you put a integer here, he may place a string. What can you do for that? Now coming to the second part, phone number, area code, prefix and suffix. So this phone number is like this, area code is like this is valid. Prefix is like this for any number, 200 area code 99 and 200 prefix from 99 as it is being seen. So any 4 digit, okay, no problem with that. But there are invalid format also. This doesn't come under phone number. This doesn't come under phone number. If you have been given that phone number has to be like this, area code has to be like this, it has to be like this. You cannot change it. Now, area code with non-numeric character, as the discussion, the logical reasoning goes like that only, which I discussed here. So now coming to the second aspect of black box testing, we have seen equivalence partitioning. Now boundary value analysis. This is exactly what you are understanding, because the name suggests the explanation only. Boundary value analysis. So when choosing values from an equivalence class to test, use the value that are most likely to cause the program to fail, not like every value. Choose that value which is going to fail, because you are testing it and you have to do anything to fail that program, to fail that software. So error tends to occur at the boundaries of equivalence classes rather than at the center. So if this is the first, you have to see that the valid area code is not there or not. So this is not valid area code. This is the valid area code. Now what you have to do, you have to check at these points, 299. Checking at 770 will not give you a proper idea. Though 770 is also important, but you check on the boundary, because this is where the program fails. So in addition to testing center values, we should also test boundary values, means right on the boundary, very close to the boundary or either side. This you need to check. So this now boundary value analysis example I must show. Before that, let us see it graphically. Create test cases to test boundaries of equivalence class. Now we have these boundary values. See the region which we have marked, the points which are lying on those region exactly are the values of our concern, or the inputs or test cases of our concern. So let us come to the example. These are the values, these are the boundary values. What we will do is, we will check at the boundary cases. Minus 99, okay, this is fine. But let us go to minus 100. 99 is fine, let us go to 100. And all those values which comes under the purview of excellent test cases, we have to check them. And here also the same explanation goes. You need to check area code below 200, above 1999, and if, for example, it is given suffix is any four digits, then you have to check for 3 digits also and 5 digits also. Means one minus and one plus. So numeric values are often entered as strings, which are then converted into numbers internally, because internally all combination and all permutations are seen as numbers only for as far as computer science is concerned. So these conversions requires the program to distinguish between digits and non-digit. A boundary case to consider, what can be the boundary case? That will the program accept this or this as digit? Okay, this and this as a digit. This is the boundary value analysis. This is how you are going to do it. But there is mainstream usage testing also. Don't get so wrapped up in the testing boundary cases. Then you actually neglect the test not to test the normal input value. So do check those values which are valid. So this was the idea about black box testing, but we will see more in the next part. Thank you so much. Take care of yourself.